All right, so more about electric current. Electric current can cause electric shock, and a shock results from electric current passing through or to the human body. And it can only happen when there's a potential difference between the two parts of the body. So if you've ever seen a bird standing on a phone wire, there isn't a potential difference across their body, so they're not going to get shocked. Now, if he took this foot and put it on this other wire, that would be a different story. Or if you were, say, working on a ladder and the ladder was metal and you were to touch this wire, then the current could flow from the wire through you to the ladder to the ground, and that would be a bad thing. Um, Now, if you're in the bathroom and you're drying your hair with a hair dryer and the floor is wet and your feet are wet and your hair is wet, the chance of being shocked by that hair dryer is much greater because you have a much lower resistance when everything's wet. If you've ever touched a 9-volt battery, just with the battery, take the poles of the battery and touch your fingers, and you won't feel any current. You won't feel a shock. But if you take that same battery and touch it to your tongue that is wet, and the nerve endings on your tongue are more sensitive than your finger, you're going to feel a shock. And you can try that. It's perfectly safe. It feels kind of weird. It tastes like lemons to me. Electricity tastes like lemons. Um, all right. And then what's the role of this third prong on a grounded um, electric circuit? Uh, it is called the ground, and it's meant to take any buildup of electric charge caused by these two prongs and siphon it to the ground so that it's not going to produce a shock. Okay. Now, two different types of current that can flow through a circuit. There's direct current, which flows in one direction. So here we have a graph of direct current, and it's flowing in a single direction. Batteries produce direct current from, um, and this is going to be part of the confusion. We know that electrons are going to be repelled by the negative and attracted by the positive. So, in a physics sort of way, that's what's happening. Oh, shoot. Um, but conventional flow, as we talked about a second ago or in the last chapter, it flows, electric fields flow from the positive to the negative. So, conventional flow versus actual physics flow are kind of backwards. So I'm not going to ask you about that, but just know that direct current flows in a single direction. Um, Solar panels produce direct current. Um, all right. Now, alternating current, if you look at this graph of alternating current, it's kind of a sine wave. Okay, so it actually pulses back and forth in two directions. And it's produced by generators. And basically, when a generator produces electric current, you see here, you have, and this is an oversimplification of how a generator is built, but you have a moving magnet, and actually they're caused to rotate or to spin, so the polarity of the north-south alternate. Consequently, the direction of the current that's produced alternates. So anything that is produced by a generator or like the alternator in your car is alternating current. Okay. Most AC circuits, alternating currents are in North America and around the world. Most are 60 cycles per second, 60 hertz. And technically they're 110 volts, although we call it 120. Large appliances like stoves and dryers and air conditioners and refrigerators sometimes require 220, which basically has the positive and negative of the circuit. So we're getting, you add those together and you get twice as much. Now, years ago, there was a big battle between the two titans of the electrical industry, Edison versus Tesla, on which would take over the world as the mode that we would produce electricity. And as is often the case in a capitalistic system, the way to make the most money is going to be the way that it's going to work out. So with direct current, the drawback with direct current is that it cannot be transmitted over large distances, too much resistance. So you would need a direct current power plant in each locality, like each neighborhood would need a direct current plant, power plant. Or currently, solar panels, solar energy, direct current. But back then, and even now, we have power companies that want to provide electricity for us. So you want to have a single power plant that can provide electricity for an entire region. Consequently, Tesla and his design of electrical generators at Niagara Falls could produce enough electricity for the entire Northeast, which is where a huge population base is. So consequently, at least in that sense, Tesla won out over Edison, and there's a whole backstory, interesting, fascinating backstory between the animosity between these two. They started out as friends. Edison was a mentor of Tesla, but Tesla was probably understood electricity a lot more than Edison did, and Edison didn't like it. So the way he showed that was by kind of backstabbing and just doing bad things towards Tesla's designs and whatnot. So anyways, I wish I had more time to go into that, but it's a really fascinating story if you ever want to look up the backstory between those two. Now, converting back and forth between alternating and direct current, we'll talk about how you can take an alternating current and produce a direct current from it. And one is with the use of diodes. Diodes are basically one-way valves that only allow current to flow in one direction. Okay, so if we can put a diode in, then we would only get these flowing, but you would see that there would be gaps, so the current would be pulsing. So then you have to put capacitors, which can produce that current at a quick blast. And if you put capacitors that can fill in these gaps, then you would still have pulsating current, but then you could put more diodes in to smooth it out even more. Okay, and then so that's what's happening inside of these adapters and rectifiers. So you have like the scales in the lab have these adapters because they run off of direct current. Also, you don't want a full house current to be running through those things. Yeah, and then inverters can take direct current, like from solar panels or car batteries, and can produce alternating current from it. So if you have, say, solar panels and a bank of batteries to store the energy, but you want to run your refrigerator off of it, then you could have an inverter to make those changes. Okay, so what exactly is electric current? So a lot of people talk about the flow of electrons and the flow of current as being interchangeable, but they're really not. Current are actually the flow of electric fields, and electric fields are produced by the electrons, but they're not the electrons themselves. So we looked at fields in the last unit, and you saw that there were fields just kind of emanating around anything that has a charge. So there are electric fields just emanating in the air surrounding this battery. Um, it just so happens, though, if you take a conductor and hook it up between one pole and the other, then you can get a current. You can get those fields to flow at super high speeds through that conductor. Okay, that's electric current. So it's kind of like a light wave through a medium. Um, so when light flows through glass, remember the Goldberg model? Um, so electric fields can flow through a medium like a wire in a Goldberg model. Okay, and the electrons are what transmit and produce that electric current, but they're not the electric current themselves. If you look at this diagram, the electrons are actually flowing and they have random kinetic energy. They're being shared evenly throughout the conductor, but the current flows in a single direction. Okay, at least in direct current. Um, so in direct current, they have what is called electron creep. They have a drift speed of about a hundredth of a centimeter per second. So they're moving in constant random motion in random directions, but they're actually flowing in the direction of the current, but at a really slow speed. Um, so it would take 3 hours for an electron to move 1 meter in a conductor, whereas the current flows at light speed virtually. Okay. And then electrons in an alternating current kind of vibrate back and forth with the alternating of the current. Now, electric power is how we are billed for um, electricity usage. So electric power, if you think back to what power was in our energy unit, power, the units of power are watts, water, the units of power, haha. And it's energy per unit of time. Okay, so we can look at power as current times voltage, P equals IV, but where does that come from? Well, if you look at the units of each of these, current is charge per unit of time, and voltage is energy per unit charge. Then if we multiply those two, the charges cancel, and we end up with energy per time, which is what power is. Okay. So that's how this equation was derived. The SI units of power are watts, but we use so much energy, we amp it up to kilowatts. And then we sell energy by the kilowatt hour. And that makes sense because energy, if we look up here, if we take this equation and solve for energy, energy would equal power times time. Okay. So you might be asked how much resistance is in a 40-watt light bulb. Well, in this 40-watt light bulb, there is no resistance because it's not plugged in. But if you plug it in, then you could figure it out. You might be thinking, well, I only know one variable. Well, as is often the case, other variables might be hidden. So if you think back to what is house current, it's 120 volts. That's the voltage of the current that runs through, the push that causes the current that runs through our houses. Okay, so it's going to require two different equations, and I'm going to show you two ways to solve this. I think the easiest way is just to start with this equation. We know P equals IV, where I is the current, V is the voltage. Okay, it's a 40-watt bulb. The current we don't know, but the voltage is 120. That's house current. And so I would be 40 divided by 120, which is 1/3 or 0.33 amps. Then if we take this and plug it in here, again, the voltage is 120 and the current is 0.33, and then just solve for R. So 120 divided by 0.33